Hello, linear algebra students. This video lesson is a continuation of our discussion on linear transformations. Now consider the linear transformation T1 that corresponds to multiplying the input vector by this 3x4 matrix. Identify the domain, codomain, and range. We begin by noting that this 3x4 matrix can be denoted bracket T sub 1 to refer to the standard matrix of this transformation. Furthermore, it is 3x4. This vector here has to be a 4x1, and this is the input vector. And then the result will be a 3x1. As the input vector varies across all possible 4x1 vectors, we simply get all linear combinations of the columns of the standard matrix. Therefore, the range of this linear transformation is simply the column space. In general, that is true. Note that the range of a linear transformation T is simply the column space of its transformation matrix bracket T. We begin with the domain. The input vectors have to be 4x1, therefore the domain will be R4. Now let's do the codomain. The output vectors have to be 3x1, therefore the codomain is R3. Now we need to find a basis for the column space of this standard matrix. Using technology, we can put the standard matrix in reduced row echelon form, and we get the following. We see that there are pivots in the first column and in the third column. Therefore, a basis for the column space will be the first column and the third column of the original matrix. And the range is simply equal to the column space, which will be equal to the span of the first and third columns of the standard matrix. Well, the span of two three-dimensional vectors will be a plane through the origin. So we know that that will not be the entire R3 space. Let's examine this column space using GeoGebra 3D. I've graphed all the columns of the standard matrix, and because the basis only needs two of these vectors, it suggests that the four vectors are all coplanar, which they are. And in particular, we wind up keeping the first and third columns to form a basis. So this plane that we see here contains the two basis vectors, and this plane is the column space. Therefore, this is the range of the linear transformation. This transformation will take a four-dimensional input and transform it into a three-dimensional vector that will terminate somewhere on this plane. So the next question is, determine if the vector v is in the range of the transformation T1. If so, give one preimage. So we essentially need to determine if this vector 1, 0, 3 is in the plane that we see depicted. So our goal is to solve the following system. We are looking for a vector u such that u times the matrix will be equal to this vector v. We'll convert this to an augmented matrix as follows, and then put this in reduced row echelon form to get. Now this bottom row reveals something interesting. This suggests that 0 is equal to 1. Thus we have an inconsistent system, which means that it is not possible to obtain the vector 1, 0, 3 via this linear transformation. So vector v is not in the range, meaning it is not coplanar with the vectors that are the columns of the standard matrix. Looking at our image, the vector v is the purple vector, and from this angle we can clearly see that the purple vector does not terminate on the plane. Therefore, it is not in the range of the transformation. Okay, let's go to the next page. A linear transformation T from Rn to Rm is called onto or surjective if the codomain and range are equal. Note this occurs when the column space of the standard matrix for the transformation is equal to all of Rm. So I will use Venn diagram to help understand this. Our domain is Rn, and our codomain is Rm. And in some cases, the range of the transformation is not all of Rm, meaning that all the vectors in Rn map only to these vectors in Rm. And that is how we define range. Well, that was the case of the previous example. Looking right here, the range was a plane through the origin. It was not all of R3. But now we are saying that a transformation is called onto if the range is actually all of Rm. In this case, where the codomain and range are equal, we say that the transformation is onto, because all the vectors in Rn will map onto the entire codomain. Okay, determine which transformations below are onto, or surjective. So we have three transformations here. T1 is the same transformation we had above. So once again, I'll put its standard matrix into reduced row echelon form, getting the following. Also recalling that the codomain here was R3, and that the column space was the span of columns 1 and 3 of the standard matrix. Well, it is not possible for two vectors in R3 to span all of R3. In fact, we know the two vectors will only span a plane, which is a proper subset of R3. And since the range is the column space, we know that the range is not all of R3. So we say that this transformation T1 is not onto. Okay, let's look at a new transformation with a standard matrix that's 4 by 3. The codomain of this will be R4 because this transformation inputs 3-dimensional vectors but outputs 4-dimensional vectors. And now let's put the standard matrix into reduced row echelon form. Notice we do have pivots in each of the 3 columns. So the basis of the column space will have 3 vectors. The 3 columns of the standard matrix themselves form a basis for the column space. They are linearly independent as is. However, it is not possible for 3 vectors only to span all of R4, in the same sense that 2 vectors alone could not span all of R3. So we know that the range cannot be all of R4, so the range and codomain will not be equal. So once again, we have a transformation that is not onto. In fact, you can generalize here. If we have more rows than columns, then it will be impossible for the linear transformation to be onto, because the number of rows indicates the codomain, in this case 4, R4, and you need 4 linearly independent vectors to span all of R4, but there are only 3 columns. So there was never potential for the columns to span all of R4. Let's look at the third transformation on this page. Putting its standard matrix into reduced row echelon form, we get, well, first of all, notice that this standard matrix is very similar to T1's standard matrix with just one difference. This position right here is different from this 5 in T1. Otherwise, they're the identical matrices. But that change alone has a dramatic effect on the column space, because now we have a reduced row echelon form that has a total of 3 pivot entries. Therefore, we have 3 vectors that will form the column space, and we know that 3 linearly independent vectors in R3 will span all of R3. So in this case, we do have that the range is equal to all of R3, and we have that T3 is onto. This simply means that every single R3 vector is in the range, meaning that there is some linear combination of the columns of the standard matrix that will produce that vector. We can also generalize that if every row of the reduced row echelon form has a pivot 1, and the number of rows dictates the codomain, which we should say is also R3 here, if each row has a pivot 1, then we will have the correct number of vectors in the basis of the column space to span the entire codomain. Okay, let's go to the next page. Consider the linear transformation T3. So this is the same T3 that we've examined up here on the previous page. We've already determined that this transformation is onto, meaning that every single vector in R3 is in the range. It's attainable by this transformation. Now we're going to find all vectors u such that T3 of u gives us the vector 7, negative 4, 10. And we do this, of course, by solving a system. We will solve the standard matrix of this transformation times vector u is equal to this vector 7, negative 4, 10. So first we'll create an augmented matrix, and then we will put this in reduced row echelon form. And once again, we see that we have 3 pivot positions. The columns correspond to x, y, z, and w. So we see that y is free. The first row is x minus 2y must be equal to 7. So that means x has to be equal to 7 plus 2y. The second row reads that z has to be negative 1. And the third row reads that w has to be 0. And let's not forget that y needs to be in here and that it's free. So we'll set y equal to itself. Now keep in mind that our domain is R4, so we better have a 4-dimensional vector here. We need the components x, y, z, and w. And now we will decompose this by the constant portions of each of these variables and then the portions that are dependent on y. So our vector u that we were after is equal to, let's begin with the constant portions, create a vector out of that. So the x component has a constant portion that's 7. There is no constant in the y component, and then -1 and 0 are the constants of the z and w components. And then plus y times, and then all the coefficients of y, which will be 2, 1, and then 0, 0. So this describes all the vectors that are possible that when you input them into this transformation, you will get the output vector 7, -4, 10. And there are infinitely many. What's going on in this case is the following. We have a transformation taking R4 to R3, and we have a vector in the range. Remember, the range of this transformation is all of R3, so any vector you pick in R3 will have at least one preimage. That particular vector we picked was 7, -4, 10. And what we're discovering is that there are infinitely many vectors in R4 that will map there. So there's a whole subset of R4 that will form a preimage or a set of preimages of this one single vector. So basically we have infinitely many vectors in R4 that all map to this same vector. So one vector in R3 has infinitely many preimages in R4. Let's go to the second part of this page. Find all vectors u such that T3 of u is equal to the 0 vector. So we'll do basically the same thing, but this time we want the output to be the 0 vector specifically. So we begin with our augmented matrix with the 0 vector as the output, and then we'll put this in reduced row echelon form. And we get the following. Again, we see that y has to be free, but the x minus 2y must be 0, so x has to be 2y. Y is free, so we'll let y be itself. Z has to be 0, and w has to be 0. So we really just have all multiples y of the vector 2, 1, 0, 0. It is not a coincidence that this component of our answer above and this component right here match. And once again, we see that there are infinitely many vectors in R4 that will map to the 0 vector in R3. Reading right here, note that the preimage of 0 for a linear transformation T is simply the null space of that transformation's standard matrix. It's a set of all vectors that map to 0. But in the context of linear transformations, we have yet another word to describe this set of vectors, and that's called the kernel of the transformation T. So this red collection of vectors in R4, it is the null space of T3's standard matrix, and we're also calling that the kernel of T3. All right, let's go to the next page. Now, a linear transformation T from Rn to Rm is called one-to-one, or injective, if every vector in its range has one preimage. Okay, let's investigate what this means. We'll use a Venn diagram to make sense of this. We're back to Rn mapping to Rm, and the transformation having a certain range. And in general, the range and the codomain don't have to be the same. But in order to be a one-to-one or injective transformation, every vector that you pick that's in the range can only have one preimage. So this would not be allowed to have two vectors in the domain mapping to the same vector in the range. Not allowed if this is one-to-one. So all the different vectors in the range can only have one preimage each, somewhere in the domain. So the example above, here we had a vector in the range, but it had infinitely many preimages. So the transformation above in the previous page is not one-to-one. Determine which transformations below are one-to-one. This should read one-to-one. We have three transformations, T2, T3, and a new one, T4. The T2 and T3 that you're seeing here are the same T2 and T3 that we analyzed 2 pages ago. And then we have a new transformation, T4. So we begin by letting some vector be in the range of the transformation. So let's say that vector B is in the range of T2. And then we consider the solutions to the system standard matrix of transformation 2 times vector u is equal to this vector b that's in the range. We would do this by creating an augmented matrix and putting it in reduced row echelon form, which would have the following form. Here's the coefficient matrix, augment it with the vector b, create this augmented matrix overall, and put it in reduced row echelon form. And it's going to have the following form. The coefficient matrix, we know, reduces to the following. Reducing it separately gives us this result. But then it will be augmented, and we will have some entry here, some entry here, some entry here, and this bottom one would have to be 0 if b is in the range. If b is not in the range, then that bottom entry would be non-zero and we have an inconsistent system. But we are assuming that b is in the range, so we're assuming that it is a vector for which we have a consistent system here. But what matters is the number of pivots in the coefficient matrix. There are 3 pivots, 1 per variable of the input vector. Keep in mind that the input vectors here would have only 3 components. So we would just have x, y, and z. But because there are no free variables, we are not going to have infinitely many answers. We're going to have a unique answer. So the solution is unique, which means that the pre-image of b is unique, which means there's only ever going to be one vector in the domain that will map to this vector b that's in the range. That tells us that T2 is 1 to 1. And we can say 1-1 to abbreviate 1 to 1. Okay, let's repeat this thinking for the next 2 transformations. So we just assume that b is in the range of this transformation. And then we row reduce an augmented matrix, where the coefficient matrix is the standard matrix of the transformation. And we augment it with the vector b. And then we row reduce this. And in this case, it will row reduce. Well, the coefficient matrix will row reduce as follows. And then we'll have some sort of numbers over here in our final column. Hard to say what they are until we actually specify what b is. But what matters is that we have 3 pivot positions, but 1 free variable. This free variable means that we're going to have infinitely many solutions. So the solution will not be unique. So this will be a situation like the previous page where many vectors in the domain will map to any one vector in the range. So T3 is not 1 to 1. And now let's analyze a new transformation T4. And T4 is going to map 3-dimensional vectors to more 3-dimensional vectors. But let's assume that we have a vector b that's in the range of this transformation. And then we will reduce an augmented matrix that the coefficient matrix is the standard matrix of the transformation, and we augment it with the vector b. And when you put this in reduced row echelon form, the coefficient matrix reduces as follows. And then the augmented column will become some sort of number, and then certainly a 0 here if b is in fact in the range. If that bottom entry was not 0, then we would have an inconsistent system, but we are assuming that b is in the range. So we must have a consistent system, therefore. But notice that we only have pivot positions in the first and second columns, so we do have a free variable again. And that free variable suggests that we have infinitely many solutions, which means that the vector b, whatever it is, has infinitely many pre-images. So we do not have a 1-to-1 function here. So after seeing these examples, we can generalize. If we have no free variables, when the standard matrix is put in reduced row echelon form, then we can conclude that the transformation will be 1-to-1. But if we have free variables, then the transformation will not be 1-to-1. Okay, let's go to the next page. A linear transformation, T, from Rn to Rm, is called bijective if it is both 1-to-1 and onto. In other words, if it is both injective and surjective. All right, so to be surjective, we have this Venn diagram where the range and Rm are equal to each other. This is what it means to be surjective. And then to also be injective, it means that every vector that's in the range, so in other words, in all of Rm, has only one preimage, establishing this 1-to-1 relationship between a vector in the domain and a vector in the codomain. And this is called a bijective transformation. So we're going to summarize the 4 transformations we have been looking at so far, as well as a 5th new transformation at the bottom of this table. So this table shows all the standard matrices with their RRE forms. For the first case, we can look back at our notes, or we can simply do the analysis again. But to be surjective, we need the column space to be equal to all of the codomain. Now the codomain here is R3, because the output vectors are 3-dimensional. But we only have 2 pivot positions in the RRE form, which means our basis for the column space only has 2 vectors. And when you span 2 vectors, you cannot get all of R3. Therefore, this is not surjective. Furthermore, looking at the reduced row echelon form, if we were solving a system, notice that there would be 2 free variables. And if there are free variables, then there will be infinitely many answers every time we have a consistent system. Therefore, this is not injective. And if it's not injective or not surjective, then it will certainly can't be bijective. The only time we will say bijective is if we have a yes for both surjective and injective. Let's look at the transformation T2. Its standard matrix reduced as shown here. We do have three leading ones, three pivot positions. So all three columns of the standard matrix do form a basis, but the codomain here is R4, and we only have three vectors in the basis of the column space. Three R4 vectors cannot span all of R4. We would need four linearly independent vectors to span all of R4. So we know that this cannot be surjective. How about injective? Well, there would be no free variables if we were solving a system, which means that the solutions, when consistent, would be unique. So every vector in the range would have a unique pre-image in the domain. Therefore, this is injective. But because it wasn't both surjective and injective, it is not bijective. T3 has three pivot positions. So the column space would have three basis vectors. And since the codomain here is R3, and we have three linearly independent R3 vectors in the basis of the column space, we know that the range will be all of R3. So this will be surjective. However, when solving a system, notice there will be a free variable, and that will give infinitely many solutions every time we have a consistent system. So for any vector in the range, we will have infinitely many vectors in the domain that are the pre-images of that one vector in the range. So this is not one-to-one or not injective. So overall, it's not bijective either. T4, mapped R3 to R3, so the codomain is R3, has only two leading entries in the RRE form, so only two vectors in R3 will form the basis for the range. So the range will just be a plane in R3, which is not all of R3. So we do not have a onto or a surjective transformation here. In order to span all of R3, we need three linearly independent vectors. Two alone will not cut it. Also, there would be a free variable when solving systems. So anytime we pick a vector B in the range, there will be infinitely many pre-images of B. So this is not injective, so not bijective. And finally, let's look at a new transformation T5 and look at its reduced row echelon form. This is a 3x3 standard matrix. So this transformation does map R3 to R3. And we have three pivot positions. All three columns of the standard matrix will form a basis for the range. And when you have three linearly independent vectors, they will span all of R3. So this is a case where we do have a surjective transformation. Furthermore, there are no free variables when solving systems. So anytime we have a consistent system, we will have a unique solution. So it is also injective. And so we finally have a case where we have a bijective transformation. Now, note at the bottom that a linear transformation T is bijective if and only if its standard matrix, bracket T, is square and non-singular. Non-singular meaning invertible, which will tap us into the equivalence statements, which we'll do on our last slide of this lecture. But before that, let's go to the next page. Now, in our last lecture, we discussed some common transformations from R2 to R2 and from R3 to R3. And we'll review some of these and discuss whether they are surjective, injective, or bijective. So let's consider the scaling by k, where k is non-zero. So the result of this transformation is to take an input vector and to scale it by k. So let's say k is 2. So the input vector would simply be scaled by a factor of 2 and would have twice the magnitude. Well, if you take any vector in R2, is it possible to have a pre-image? So if you took the vector 6, 4 and say what's the pre-image of 6, 4 should be 3, 2. Right, the vector that you would start with before doubling in order to get 6, 4. So basically the pre-image of every vector in R2 would be half of that vector if k was 2. So every vector would have a pre-image. Furthermore, the pre-image would be unique. If you take a vector in R2 and do 1/2 of it, you will get a unique answer, not multiple answers. So this is a case that would be surjective and also injective, therefore bijective. Also notice that its transformation matrix here is square and has a non-zero determinant, which means that it's non-singular or invertible. Recall that we are assuming K is non-zero. And if the standard matrix is square and non-singular, then it will be bijective. Reflecting across the x-axis. So imagine the vector 3, 2, and you reflect that across the x-axis, it would become 3, negative 2. So if you take any vector in the range, you can easily find its preimage by doing the reversing that reflection. So in other words, by reflecting once again across the x-axis. So every vector would be in the range, because it can be thought of as the result of doing some sort of reflection across the x-axis. Furthermore, the preimage is a unique vector in the domain. Also, this standard matrix is square and non-singular because it has a non-zero determinant. So this is a transformation that is both surjective, injective, and therefore it is bijective. Now, imagine projecting to the y-axis. So take the vector 2, 1 and project it to the y-axis, it would become the vector 0, 1. But this transformation can only produce vectors on the y-axis. Therefore, there are vectors off the y-axis that are not in the range. So this cannot be surjective. Also, this transformation is not injective, because if you take the vector in the range 0, 2, that's on the y-axis, there are infinitely many preimages. The vector 1, 2 will map to 0, 2. The vector 2, 2 will also map to 0, 2. The vector 3, 2 will also map to 0, 2. So there are infinitely many vectors that will map to 0, 2. So this is not injective, also not bijective. Consider the rotation counterclockwise by a fixed theta. If you take any vector, can it be thought of as the result of such a rotation? And the answer is yes. Take any vector in R2 and reverse this transformation would mean rotate that vector clockwise by a fixed theta, and it would take you to the preimage. Furthermore, if you take a vector and you go clockwise by theta, it'll take you to a unique preimage. So every vector has a preimage, and every vector has a unique preimage. Therefore, this is both surjective and injective. Therefore, bijective. Now, this 2 by 2 matrix has a determinant. If you calculate it, you would get cosine times cosine, which is cosine squared, and then minus a negative sine squared. So that would just lead to cosine squared plus sine squared, which is 1. So the determinant of this standard matrix will always be 1, regardless of what theta is. And 1 is non-zero, therefore this is a non-singular matrix. Therefore, we do have a bijective transformation. Now, if we reflect around the xz plane, that means we change the sign of the y-coordinate. Every vector in R3 has a preimage. Every vector in R3 is possible in this transformation. We have a surjective transformation. The preimages would all be unique, so we'd have an injective transformation, therefore bijective. Also notice that the determinant of the square matrix would be negative 1, which is non-zero, therefore non-singular, which again confirms a bijective transformation. Now projecting to the yz plane, that just means we zero out the x-coordinate. This will not be surjective because the range here is the yz plane. It's not all of R3. So not surjective. Also not injective because there are many vectors that would map to the same element in the range. If you take any point in the yz plane, and it would have infinitely many preimages. For example, consider the vector 3, 2, 1. That would map to 0, 2, 1. But the vector 4, 2, 1 would also map to 0, 2, 1, etc. So this is not injective, certainly not bijective. And notice that the determinant of this 3 by 3 matrix is 0. So this is a singular matrix, and our if and only if statement above suggests that if you get a 0 determinant, therefore the transformation will not be bijective. We could have made that comment up here as well for this matrix. It has a 0 determinant, therefore the transformation with that standard matrix will not be bijective. And then the last one, rotations. All rotations can be reversed and reversed uniquely. So any vector, every vector in R3 is in the range, and when you undo the rotation, you get a unique preimage. Therefore, this rotation is both surjective and injective, therefore bijective. And if you calculate the determinant of this 3 by 3, you will also get 1, which is non-zero. Doesn't matter what theta is, you will still get 1. Therefore, we have a non-singular square matrix. Therefore, the transformation with this matrix as its standard matrix will be a bijective transformation. Okay, let's go to the next page. Bijective transformations, T from Rn to Rn, are invertible, meaning there exists an inverse transformation, T inverse, which reverses the mapping. So here we have a bijection being represented, where every element in the domain is mapped to a single element in the codomain. This transformation from domain to codomain we're calling T, and one example of which would be T of the vector u would produce the vector v, according to this image. Now the reverse mapping is as follows. The inverse mapping, T inverse, maps elements from the codomain and maps them back to the elements of the domain. It's the reverse mapping. And in this notation, T inverse of the vector v would go right back to the vector u in the original domain. Now note that the standard matrix of an inverse transformation is just the inverse matrix of the standard matrix of the original transformation. Find the inverse transformation of the bijective linear transformation below. Now this T5 transformation is the same transformation mentioned 2 pages ago, where we argued that it was both injective and surjective because its standard matrix reduces to the identity matrix. So this transformation has an inverse. Now its standard matrix is equal to the inverse of the standard matrix of T5. And I'll use technology to find the inverse of this matrix right here, and we get the following. So the inverse of transformation 5 of an input vector, and we'll use v as an input vector, will be equal to the matrix that we just found times that input vector v. Now we're going to give an example of the mapping being reversed. We'll pick a random input vector, plug it into T5, get an output vector, and then plug that output vector into T5 inverse and see what happens. For example, let's compute T5 of the vector 2, -1, 1. To get the output vector, we simply take this input vector 2, -1, 1 and multiply it to this matrix right here. And this gives us the result 9, 0, 7. Now we're going to reverse this mapping by plugging 9, 0, 7 into the inverse transformation. To find the result of this mapping, we take 9, 0, 7 and we multiply it to this matrix. Doing so, for the first entry, we get 9 plus 0 minus 7, which is 2. We get -9 halves plus 0 plus 7 halves, that's -2 halves, which is -1. And -9 twelfths, which is the same thing as -3 fourths, plus 0 plus 7 fourths gives me 4 fourths, which is 1. And sure enough, the mapping gets reversed back to the vector we started with originally. So if I call this first input vector u and it's this output vector v, we can see that T5 inverse of v does take us back to u. We can show that in generally, when you compose a transformation and its inverse, that it has no effect or takes you back to where you started by doing the following. T sub 5 inverse composed with T sub 5 of some input vector u. This will be equal to, well, first I'll plug u into T5, which means I multiply it by its standard matrix. And this, after I do this calculation, would give me a vector I could call v. But now I'm going to take this vector v and plug it into T5 inverse, which means I'm going to multiply this vector v by the standard matrix for T5 inverse. And this back-to-back matrix multiplication would produce the composition. Now, because matrix-matrix multiplication is associative, I can instead multiply the matrices together first, as such. And of course, multiplying a matrix with its inverse just produces the identity matrix, in this case I sub 3, and then we can multiply that by vector u, and the identity matrix times anything doesn't change it. So in the end, we can see that when we begin with u and plug it into T5, and then take that result and plug it into T5 inverse, at the end result will be right back at u again. Okay, let's go to the next page. Okay, at this point we can expand once more the equivalence theorem for square matrices. Suppose A is a square matrix with dimensions n by n, then the following statements are all equivalent, meaning they are either all true together or all false together. Furthermore, all the statements apply to A transpose as well. So the only new statement here is the one at the very bottom, and that is if A is a square matrix that's invertible, then the linear transformation that has A as its standard matrix will be a bijection, or we will say that it is bijective. I should say that injective, surjective, and bijective are all adjectives, and they all have noun versions: an injection, a surjection, and a bijection. So a bijection is simply a linear transformation that is bijective. Now consider the 12 statements above for the matrix below. So we have some matrix A, it is square. So it's easiest first to go to statement 3 and just calculate the determinant of the square matrix. And if we do that in this case, we do get negative 12, which is a non-zero determinant, which means that statement 3 is true. That means all 12 of these statements are true with it. So let's kind of see how statement 12 flows from some of the other statements. If I take statement 9, now statement 9 is a joint statement. It says AX equals B is always consistent. First of all, let's assume that A is the standard matrix of some transformation we'll call T. Because A has a non-zero determinant, we know that AX equals B is always consistent. That just means that no matter what choice of B we make, that we will have a solution. That means every vector B in the space Rn is in the range. That tells me that this transformation T is onto, or surjective. The second part of statement 9 says not only is it always consistent, but the solution is unique. So the solution would be A inverse times B. So every vector B in the range of the transformation has a unique preimage. That tells us that T is 1 to 1. So you take both parts of statement 9, and it leads to T being both onto and 1 to 1, and that therefore bijective, and that's what statement 12 is saying. Furthermore, I want you to observe that if number 12 is true, in other words, if T is bijective, and we know that every linear transformation maps the zero vector to the zero vector, and because it's bijective, we know that the zero vector can be the only preimage of the output zero vector. So that means the null space of the standard matrix is just the zero vector, which in new terms, we say that the kernel of the transformation is just the zero vector. It is the only vector that will map to the zero vector, which means that the null space of this transformation matrix, which is our matrix A, is also just the zero vector, which means that the nullity, which is the dimension of this null space, is 0. And these are statements 5, 6, and 8. We could go on and continue to talk more about the connections between all of these statements, but now we have a list of 12 statements that are either true together or are false together. Okay, this concludes our discussions on linear transformations.